is the notion of recency to figure out if a page is important or not. The more recent it is, the more important it is. The less recent, or the one that you've not used in the longest time in the past, is probably also likely to be the least important. That is, if you've not used something a really long time ago, then you're not likely to use it in the near future. Okay, so that's the general idea. So it uses past behavior as an estimation of future behavior. Okay, so we're going to use two bits in this case. We're going to use the reference and modified flags. So remember that reference says that a page was read in a given time window, and modified says the page was written. If it was referenced or modified, that means the page is important. And what we're going to do is essentially assign a set of priorities. Not referenced, not modified is the least important. Not referenced, but modified, that is, it's not been recently used but was written to at some point, is the next important one. So it's the one that you would replace the next. Then there's referenced and not modified, and finally there's referenced and modified. If you look at it, in this case we are prioritizing not modified over modified. The reason is that when you evict 30 pages, you need to write it back to disk. So it's on the critical path, it probably takes longer. So your preference is always for things that are read but not written to. Okay, and within the things that are read but not written to, we're going to prioritize things that were referenced recently compared to things that were referenced in the past. And if there's more than one page in a given group, let's say group 1, then we randomly choose a page. Okay, so the intuition behind this is that we want to replace a page that's not been referenced or modified. So always from level 1. The next one is FIFO, which, as its name indicates, is pretty straightforward. It tries to throw out the oldest page. So let every page kind of try to live in memory for the same amount of time. It tries to do that. And so what it's going to do is going to throw out the page that first came in, right? So it's going to try to be equally bad or equally good across all pages. This is really bad because it has no notion of recency or usage. So for example, the page that you brought in first, you may be referencing it frequently. In such cases, FIFO, if it throws it out first, then it's a bad design because essentially you're throwing out something that's important. Second chance is a variant of this which gives recently used pages a second chance. Okay, so let's look at FIFO is really bad, so second chance is a variant of that. So this one essentially is the LRU stack. So this is the least recently used, so it goes in the opposite direction. So if you look at the stack, A is the least recently used, so this has the first priority to be replaced. This is the number 1 candidate. Okay. So what we're going to do is we're going to iterate over this list, and if the oldest page has its reference bit unset, r equals 0, then it probably wasn't used in the, or it wasn't used in the least in the recent time window, and so it becomes your candidate for replacement. If r equals 1, then it probably was used in the recent time frame. So what you do is you take it and you move it to the back of the list. So if you look at it, the list that looked like this becomes like this. So A goes to the back of the list, right, in this case, and the next candidate is B. And so you keep looking at it, but what you also do is you clear the bit so that if you iterate over this at least once, then you would find at least one page to replace. So along with moving it to the back of the list, you also clear the R bit so that you'll find at least one candidate in case all of them were referenced in a short time. The next one we look at is the least recently used algorithm. This is pretty common across most systems that manage a cache or manage a finite amount of memory. So with least recently used, what we're going to do is we want to replace a page that has been used for the longest time. So programs in general have something known as locality, which is a property. And if a page hasn't been used for a while, it's unlikely to be used in the near future. So it appears that LRU would be a good approximation of OPT. So what it tries to do is use past behavior to dictate what's going to happen in the future. So it tries to look at, so remember that we earlier looked at not recently used, right? So least recently used is a more precise version of that, which tries to identify the one that was used the longest time ago. So not recently used does not necessarily need to be precise. You just need to make sure that you don't replace something that you recently used. Least recently used, on the other hand, has to absolutely identify the one that you used a long time ago. The main cost associated with least recently used is, remember that in order to check recency, every access to a page or any page in the system has to update this list. So the list must be updated on every memory reference, right? Only then can you precisely maintain the least recently used status. And if you look at it, not recently used does not need to maintain this. Least recently used is more accurate, but it has to be updated on every memory reference, which kind of makes it impractical. So in practice, most people approximate LRU using some scheme. In order to illustrate the difference between FIFO and LRU, for example, versus OPT, what we're going to do is take an example. So our overall memory size is 3 frames. So we have 3 frames in this system, okay? And this is your reference list. So this is the order in which the references happen. So time goes left to right in this world. Okay. So we first reference page A, we reference page B, then we reference C, and then we get back to A. And if you get back to A, you still have it, so that's okay. You reference B again, that's still a hit. And then you reference D. Now there's only space for 3 pages. You've got A, B, and C as candidates. The question is, what are you going to replace? Okay. So in FIFO, you replace the one that came in first. So in this case, D replaces A. And then unfortunately, you reference A again. So A, the one you just replaced. So you got to bring A in again. So this is a page fault. This is a page fault because when you first reference D, you got to bring it in. And then you referenced A, but you threw out A recently. So you got to bring A in again. And then you reference D is a hit, but reference B is a miss because A replaced B. The last time you brought in A, you threw out B, and so on and so forth. Okay. So if you look at it, we have a cache size of 3 page frames. The accesses were as shown. And if you look at the total number of page faults that FIFO had, you had 7. So when referencing D, replacing A was a bad choice, right? Because you needed A in the near future, but you didn't really pay attention to that. You just thought that because A was referenced a long time ago, essentially it was the first one that he brought in, it would be the first candidate to replace as well. You were fair, but you lost out because the access stream itself is not uniformly distributed. Okay. Now let's look at what OPT would have done. So in OPT's case, with the same reference stream, you would land up with 5 page faults, because when you reference D, you look ahead, okay? And you look ahead and you find that amongst your candidates, A, B, and C, C was the furthest away. A you reference within 1 page frame, B you reference within 2, but C is the furthest away in the system. So in such cases, D replaces C, right? And subsequently, A and B are hits. D is also a hit. But then when C happened again, it didn't have space. So again, at that point, you look far ahead, and you look into the future, and you figured out that A was a good candidate. So then C replaces A. Okay. So when you replace a page at any given instant, you look furthest into the future. Okay. So let's look at what LRU would do in this case. It tries to make the same decisions as OPT in this case. For example, when you have D, it turns out that the least recently used is C because A and B were referenced. So you look backward. So LRU looks backward while OPT looks forward. Okay, that's the biggest difference. So LRU looks backward and finds the furthest reference. In this case, that's C, so it's all fine. But let's look at another stream where LRU does not work. Okay, so when does LRU perform badly? So here's a stream where I essentially iterate over this, right? So I access ABCD, then I access ABCD again, and then I access ABCD again. So here's a loop, right? So in this case, the least recently used is also the one that will be referenced in the immediate future. So when D wants to replace the least recently used, which is A in this case, it turns out to be the one that will be that'll be used the first into the future, right? So in some ways, it's the exact opposite of LRU. So in this case, if you look at it, D makes a bad decision of replacing A, and then you find A, but then A makes a bad decision of replacing B, which turns out to be the one you need in the near future. All right, and then B replaces C, C replaces D, so on and so forth. Right. So in this case, LRU is really bad. LRU is the same as FIFO in this case, and every reference is a page fault. OPT does much better because when you have D, you look forward and you see that C is the one that's the furthest away. So because it's the farthest away, it's the one that it chooses your candidate. And because of that, A and B turns out to be hits. And C, when you access C, it replaces B, and your overall, you only have like, let's say in this case, 1, 2, 3, 4, 5, 6 page faults, right? Compared to the one in the previous case where every reference beyond the first 3 were all page. Every reference was a page fault essentially. The links I've shown you here, animations, and which kind of highlight the differences between FIFO, OPT, and LRU. I would encourage you to go take a look at these. So one of the interesting desirable properties you would like to have in your system is that the more memory there is, the miss rate goes down. That is, your efficiency is not lower with more memory. So it seems intuitive that this should always be the case, right? But some algorithms do not have this property. And an example of this is FIFO, where for certain reference streams, even if you have more memory, you could land up with more page faults. This is because the decision that the system makes with more frames is quite different from the one it would have made with lesser frames, right? So in some cases, what we really want is a curve like this, where it's a monotonically decreasing curve, right? But things like FIFO, this is not necessarily true. For certain access patterns, it may actually go up, right? We don't want that. We always want it to go down, right? Thankfully, LRU does not have this property. So to illustrate this example, both LRU and OPT do not suffer from this anomaly. For FIFO, it may suffer for some reference stream. I'm going to show you one particular reference stream. Right? So let's take a look at this. So in this case, I'm going to access ABCD, ABE, ABCD, and E again. Okay. So if you look at LRU or OPD, when you go, or let's look at FIFO. Right? So when you go in FIFO from 3-page frames to 4-page frames, so you have more physical memory now. Technically, you would expect less page faults. Okay, but in this case, what happens is up to this point, it's actually better. So up to this point, you're able to store everything. Except, but notice that now your stack has changed. So when E shows up, okay, the candidate that you have normally replaced would have been D. Right? In this case, E would have replaced D. Right? D replaced A, E replaced D, so we have 2 page faults. In this case, E replaces A. Okay, a stack, the one that's prioritized has changed. And unfortunately, it just so happens to be that A is the one that's most recently needed in the future. And so, you have a domino effect, and when A is accessed, it replaces B, and then because of FIFO property, and B, it turns out that B is the one that's most recently needed in the future, and so on and so forth. And so overall, if you look at it, we added more memory, and we actually landed up with 10 page faults, right? And LRU and OPT do not have this trouble. They will always ensure that if you have more memory, then you'll have less page faults. That is, they are monotonically decreasing. But this is not the case with FIFO. Okay. So how do you implement LRU? So one option is to keep a timestamp on each reference, but obviously this needs to be updated every time a reference happens. You keep a list of pages ordered by time of reference, but then the challenge is that the list needs to be manipulated on every reference. And both of these are expensive to implement in reality. There are some hardware techniques, but in most cases, software techniques, you either use not recently used algorithm as an approximation of LRU, and then you use aging and clock algorithm. And we'll look at those in a second. Okay. So not frequently used aging and clock are all approximations of LRU. So not frequently used, you use a software counter with each page. So every page has a software counter. At the end of each clock period, and the clock period could be anything that you define in the system, typically it's 10 or 20 milliseconds, the operating system scans all pages in memory, so it iterates over it. For each page, it checks the reference bit, okay, if it was referenced in the most recently elapsed time window. And if it is, and if the reference bit is 1, it's just added. In fact, you don't even need to check it. The reference bit can be either a 0 or 1, right? So you add it to the counter. So the counter in rough keeps track of how often each page has been referenced. So it keeps a count, right? So it keeps a number of how often it's been referenced. So when a page fault occurs, the one with the smallest counter is chosen. So recency is a notion of time. Frequency is a notion of number. So how many times do you access a certain thing? And so when a page fault occurs, the page with the smallest counter is chosen. The trouble with this is that it never forgets. So pages that were frequently referenced during an initialization period, for example, would no longer be, but are no longer needed, would appear to be frequently used. So imagine a page that was accessed a lot upfront, right? So let's say A was accessed like 100 times, right? And then subsequent to that, it was never accessed, right? No accesses to A. In such cases, you would hope that A, eventually goes down the priority list, but it would take a long time before other pages catch up, and other pages may never catch up, right? Eventually they may, but it take a long time. And so this is a challenge with not frequently used. So aging takes care of this challenge with not frequently used is that it never forgets. So the idea behind aging is that you gradually forget the past. A k-bit software counter is associated with each page that's initialized to 0, and you shift all counters to the right before the R bit is added. So you have some notion of history, and if you keep shifting to the right, that means you forget the oldest history. So eventually, if a page is never accessed, by shifting it right, its priority will fall down to 0 and ultimately fall down, it'll be chosen as a candidate for replacement. So if you look at the way this whole thing works, it's easier to illustrate with an example. So in this case, I've shown you 5 pages. So what I'm going to do, and I'm going each of these hashed lines indicates a clock period, right? And in this given clock period, I'm going to add the following reference. For example, page 1 was referenced, page 2 was referenced, page 3 was not referenced, and page 2 were not referenced. So page 1, 3, 4, 5, and 6 were all referenced. Okay, and in this case, sorry, if you start with the index 0, then pages 0, 2, 4, and 5 were referenced. Pages 1 and 3 were not. Okay. So if you look at it, we start off with the following reference. Let's just follow page 1. So page 1, and here I'm using an 8-bit field, which means I'm trying to remember the last 8, the history of the page during the last 8 clock periods. Okay. So what I'm going to do is I'm going to shift it to the right and then concatenate it with the current history, which is this page was referenced. So as you can see, the top 2 bits are 1 for page 0. And so on and so forth until you hit the 5th clock period when the page wasn't referenced. And in such cases, if you look at it, we shift it and then we concatenate it, and the topmost is 0, which reflects the most recent usage of this page. So as you go towards the left, you get the most recent history, and as you go towards the right, you get the least recent history. And as you can see, as we shift, because we shift right, the least recent history is kind of dropped on the floor as we're going along. And so this helps you gradually forget that a page was frequently used, at the beginning, but then may not be anymore. So aging versus LRU. Aging has a finite history of memory. So essentially, it cannot distinguish between a page that was referenced 9 clock periods ago versus 1,000 clock periods ago. Okay, so if the counter has infinitely many bits, if we can remember things forever, then it effectively implements LRU exactly. And if you look at in current, modern systems, 8 bits are, remembering 160 milliseconds, if your clock period is 20 milliseconds, of history seems perfectly adequate for most systems. A variant of the second chance algorithm that's implemented in Linux is known as the clock algorithm. So remember the reference bit in the page table entry, which indicates if a given page was referenced in a given clock period. So what we do first is we clear it at page fault events. I'll describe how the algorithm first works and then try to give you an intuition as to what it's trying to do. So what we do is we take all the physical frames in your system and you arrange it on a circle, okay? With imagine there's a single clock hand that's moving between these pages. On each page fault, we advance the clock hand, okay? Not on a real time, but on each page fault. Page faults occur over time. So if you have a system with no page faults, then the clock will not be advanced at all. But if you have a system with a lot of page faults, then the clock is advanced more frequently. When the clock hand is advanced, we also check the reference bit. If the reference bit is set, it's used recently, we do not choose such a page for replacement as a replacement candidate, but we clear it and leave it alone. If the reference bit is unset, then it indicates that the page wasn't used in the least recently elapsed clock period, and so it becomes a selected candidate for replacement. Note that if all pages are still used, we will still find a page eventually, because the clock hand will be moving one at a time. As it keeps clearing, the next time it iterates over the loop, it will find something that's free. So there are a lot of interesting design issues that set up in the system. So what if the hand is moving slowly? So this means that there are not many page faults, and we need to find a page quickly. If the hand is moving quickly, it normally means there are a lot of page faults. There are a lot of reference bits that were set. That is, all pages were equally used for the same, or how to have equal importance. An example of animation of the clock algorithm can be found at this link, and the username and password are listed at the bottom. A variant of the clock is essentially to use the modified bit, M bit, instead of the reference bit. So this gives more importance to writes over reads, and it ensures that written pages do not get replaced by mistake. A variant of the clock algorithm is the nth chance algorithm, which essentially gives each page n chances. So OS keeps counters per page as it sweeps. On a page fault, it checks the reference bit, and similar to the previous algorithm, similar to the clock algorithm, the baseline clock algorithm. And if the reference bit is set, then it also sets the counter to n. If the reference bit is unset, then you decrement the count, and eventually when the count reaches 0, you replace the page. Note that every time the reference bit is set, you essentially promote the page back to the maximum value of n. So then it takes a subsequent another n chances before the page is eventually replaced. So this means that the clock has to sweep by n times. An interesting design issue with this is, how do we pick n? The larger the n, the more chance we give a page to be considered as important. And it's a better approximation of LRU. And typically n equals 1000 is a good approximation. The smaller the n, the more efficient it is, because it's more likely that you're going to find a page quickly to replace. Otherwise, you may have to look for a long time before you find a free page. And if you look at dirty pages, and if you think that replacing dirty pages is going to cost you more, then we give them a more chance. So for example, clean pages could have n equals 1, and dirty pages could possibly have n equals 2. So twice the priority of a dirty page. Sorry, a dirty page has twice the priority of a clean page. The next thing we're going to look at is allocation of page frames. We looked at a lot of different algorithms that are used for replacement. Okay, so what we're going to look at next is, how do you figure out how much memory a given process needs, and you allocate the space for it. So the goal is to bend physical frames or memory among different processes. So the simple question is, does every process get the same fraction? Clearly not, because different processes require different amount of memory. Should we completely swap some processes if they do not have enough memory required? And one important thing to remember is that processes also need a minimum guarantee, so that in order to ensure that all processes that are loaded can make forward progress. An example of this, it's not so common anymore, is things like the instructions on IBM 370, where a given instruction needed 6 pages. So in this case, what it was a string move, and the instruction itself was 6 bytes, might span 2 pages. The from could also span 2 pages, and the to could also span 2 pages. So in this case, you needed to ensure that the every process had at least 6 pages, lest it have an SS move instruction. So if the process had an SS move instruction that just so happened to be need 6 pages, and you didn't vend out 6 pages to the process, then it'll keep page faulting repeatedly and will never make progress, right? And so minimum page guarantee is something that the hardware designer tells the operating system about. There are lots of different scopes for considering replacement in conjunction with allocation. So one is you could select replacement from the entire set, right? You look at all the pages used by all processes and try to find the least important one. This obviously achieves effective utilization. On the other hand, each process could also select from its own set of frames, in which case you achieve effective performance isolation, guaranteeing that no process could trample upon another one. The problem with global replacement is, what if we had a malicious process that just accessed a lot of memory? In such case, if you use global replacement, what it's going to do is essentially force other processes to run slower, right? And so local replacement in such cases takes care of ensuring that if there's a malicious process, it affects only itself and not other processes. So let's look at fixed set or priority-based allocation. So there are a number of schemes to allocate space to different processes. One option is to just give every process the same amount of memory. Another one is priority, which is you look at the priority of the process before allocating. The most interesting one is proportionate, which is you allocate it according to the size of the process. And so if you look at every process and you look at the amount of frames it needs, and so you use the following equation where you do a proportionate replacement, right? So you look at how much each process is compared to the total, and then you vend out memory in the same level. The hard challenge is, how do you estimate the size of each process? And so that's where working set comes in, and we look at that in more detail. So the general idea behind allocating more memory to a process is, can we reduce capacity-related misses by changing the number of pages in the application? So if you give it more frames, would its page fault rate go down, right? So you want to obviously operate in this knee point, which is, if you gave it more space beyond this point, it does not dramatically reduce the page fault rate. But if you give it anything less than this number, then the page faults dramatically increase. So what you want to do is find this knee point in the curve where giving it that many number of page frames is just right, and you don't either lose performance or you don't gain too much, moving away from that optimal point. What happens if you move away from the optimal point is that if a process does not have enough pages, the page fault rate is very high. This leads to overall low CPU utilization, and the operating system spends most of its time swapping to disk. And thrashing essentially is a process where most of the time in the system is spent swapping pages in and out. The question is, though, how do we detect thrashing? So for this, we got to understand locality. So the locality in the memory reference pattern is essentially the fact that programs exhibit a certain well-behavedness as they're running. So essentially, this is known as temporal and spatial locality. So if you look at temporal locality, essentially it says that the pages that you accessed in the recent past is what you would access in the recent future, or pages that are likely to be in temporal space, in time, are likely to be clustered, accesses to pages, okay? And if you look at spatial locality, that's essentially saying nearby pages are likely to be touched. So if you look at the page numbers 24 and 22, they are frequently accessed together all the time, okay? So if you look at 30 and 32, it exhibits the same behavior. And if you look at each page itself, For example, page 30, it's likely to be accessed in a nearby time window. In this case, this is execution time, right? And then it's not accessed for a while, and then it's again accessed together. Okay, and so this is known as locality. And working set essentially defines the minimum number of pages that are needed for the process to behave well. So if you do not have enough memory for the working set, this leads to thrashing, and it's better to swap out a process. So let's look at what the working set model itself is. So our goal is to estimate how much memory a given process needs. So in this case, the working set window is a fixed number of page references. For example, let's say 10 million references. The working set is the total number set of pages that are referenced in the most recent time window. So it depends entirely on how you define a time window. Okay, so in this case, we've defined it as, in this case, the time window encompasses 5 pages, but in this other case, it encompasses only 2 pages. So if your delta is too small, then it will not capture the entire locality. If it's too large, it captures several localities, right? So if it's infinitely long, then essentially it captures the whole execution of the program, which is clearly does not give you an idea of how much space a given process needs at any given instant. So essentially there's something known as total demand. So the question is, how do you know what the demand frames are? Okay, so delta has to be chosen carefully. If the number of demand frames is greater than m, the amount of memory available, then this leads to thrashing because the process does not have enough memory to run in an optimal fashion. And so it's better to suspend one of the process, wait until D is less than memory, and then run this process. So you never want to run a process in the mode where the number of pages it demands is greater than the total amount of memory. Finally, an interesting question is, what about compulsory misses? So these are misses that occur when the page is seen for the first time. So pages that are touched the first time, you don't know what's going to be touched, and so that's still on disk and you got to bring it in. In a lot of cases, this may be pretty common. For example, videos or movies or music, where you're not really doing too much work on each given piece of data that you bring in, and you're just going along and bringing in more data. In such cases, most of the misses are due to the fact that you're touching every piece of data just once. So you can essentially do a couple of different things. One is you can do clustering, which is on a page fault, you bring in multiple pages around the faulting page. And so in this case, the system's efficiency improves because you're bringing pages that you think that the application may want in the future, and it just so happens that those are the ones the application also wants. Okay, so the working set tracking essentially is you use the algorithm to keep track of the working set of the application, or when swapping a process back in or out. And what you can also do with working set tracking is swap, as you keep track of it, the next time you bring the swap process back in, you could also bring in all the pages that it needed in the last time it was running. So this ensures that you don't have to track or keep track of what the application is doing recently in order to figure out what's going to happen. You kind of have an idea of what it was touching in the past, and so you use that to kind of prefetch. So maintaining working sets are quite simple. So all you got to need, again, is a shift register where you just keep track of unique pages. So note that every page in the shift register is unique. Okay. So you insert the most recently referenced page number on the right, and the set of page numbers in the shift register essentially is the effective working set. It's too expensive to do this for each memory reference, on the other hand, because every time memory is referenced, or any data is referenced to any of these pages, you got to push it into the shift register. Okay. So since it's not practical to keep a history of all the memory references or as a function of memory references, we can use a new working set definition as a window of time. So just to note, this is not wall clock time. This is the time that the process actually is actively running for. So we use the current virtual time to denote the start of the process. And based on that, we look at a given chunk of time when the process was running, and we look at how many page references happened in that given window in order to give an idea about what the working set size is. So I'm going to tell you how to use the reference and modified bits in order to estimate the working set. So remember, the reference bit of the page table entry is cleared on every clock period. Okay, assuming that the working set spans tau milliseconds over this clock period. On every page fault, the page table is scanned to look for a suitable page to evict, and we look at the reference bit. If the reference bit has been set in this last clock period, it's part of the working set. Okay, we update the time of use to the current time, and we proceed. If the reference bit is set for all pages in memory, then we pick a random page. Okay, this is a corner case. If the reference bit is unset, okay, that means that the page wasn't recently used. The last time that it was touched would be noted down as part of time of last use. We calculate the difference between the current time and the time of last use. And this kind of tells you a notion of recency, how stale or how up to date is the importance. If the age is really high, then the page is no longer considered to be part of the working set because the last time it was touched was a really long time ago. If the age is not that high, then the page is still in the working set because we still don't know if it was not referenced a long time ago. So we don't know if the information is stale or not. And if all pages in the physical memory are still in the working set, which is a possibility because all pages were equally likely to be used, then the oldest one is simply chosen for eviction, or the first one that was brought in. Okay. So in this case, we're going to use a reference bit. We are also going to use a notion of time with each page. Okay, and this one indicates the current time. Right. So this one indicates the current time, and this one indicates the time on each page. So we scan all pages. If the reference bit is set, we set the time of last use to the current time. So for example, in this case, if the reference bit is set, we would say updated to 2204. Okay. If the reference bit is unset and the age is greater than a certain number, so for example, in this case, 2014. This also okay. So for example, this case, this one's age is like 1200. Okay. And if you look at this one's age is like 800. Okay, so 1200 is probably, let's say that tau was 1000. So 1200 is clearly beyond the limit. Right? So in this case, we would be choosing this as our candidate for replacement. We would give this one more chance. So it's possible that then as the virtual time in the next clock period, this could get referenced, and then this would be updated. So the working set clock algorithm is a variant of the working set. The working set algorithm scans the entire page table every time a page fault occurs until the victim is located. So with the clock algorithm and the working set algorithm, first of all, the clock hand moves only on page faults, not based on time. And essentially, you arrange the physical page frames in a circle with a single clock hand, and you advance the clock hand on page faults, not real time. So if there are more page faults, then you start tracking things more frequently. Okay. In such case, you check the reference bit, and if the reference bit is set, then it's used recently, you clear it and leave it alone. If it's unset, you need additional checking for each page, and then you look at it. The algorithm is very similar to the one which uses time, except that in this case you advance the union page fault. So the worst case, it's the same as the working set algorithm, but in the average case where the number of page faults is fewer, this is much better. So to summarize, we looked at as part of this segment, we looked at a number of replacement algorithms, which essentially look at the notion of how do you figure out which page is is the least important, and we can replace. So all of the algorithms will be compared to the baseline of OPT, which is our algorithm that looks completely into the future in order to figure out what to replace. FIFO and LRU are all variants of this. LRU is the most common one, which uses past history to kind of estimate which pages are not important. But full LRU is hard to implement. And so what most systems really implement is an approximation of it. There are a few variants of this. So there's not frequently used, which uses frequency, or how often a page is accessed in order to have a notion of how important it is, as opposed to recency, which looks at the notion of time. And then there's clock algorithm, which all uses a clock hand and advances on page faults to figure out which pages are important and uses the references bits. And there's nth chance, which is a variant of clock algorithm, which gives a page more chance to be considered as important and does not replace until it absolutely knows that it's not important. Then we looked at working set, which looks at how to estimate the amount of memory that a given process needs. And we looked at what happens if we don't give a process the amount of memory that it actually needs.